Hi students, in today's class I am going to explain about fundamental theorem of arithmetic from the chapter real numbers. Mainly this theorem is related to prime numbers and composite numbers. Now let us see what is fundamental theorem of arithmetic. Every composite number can be expressed as a product of primes, and this factorization is unique apart from the order in which the prime factors occur. Now you can check here every composite number. Here composite number expressed as a product of primes. This mainly relates the composite numbers and prime numbers. Let us check this by taking some numbers. The first number is 1, and this is neither prime nor composite. We know that. Now 2 is a prime number. 3 is also a prime number. Now 4 is a composite number. Now 4 we can write as 2 into 2, as 2 is a prime number. That means 4 are expressed as a product of primes. Here 5 is a prime number. Now 6 is a composite number. Which one? We can write it as 2 into 3, where both are prime numbers. 2 is a prime number, 3 is a prime number. That means 6 can be expressed as a product of primes. Now the next number is 7, which is a prime directly. Now 8 is a composite number. Now 8 we can write it as a 2 into 2 into 2. All are primes only. This one we can write it as 2 cube also. Means 8 can be expressed as product of primes. 9 again is a composite number, which can be written as 3 into 3. That is simply 3 square. Therefore 9 also can be expressed as a product of primes. The next number is 10, which is a composite number. I can write this one as 2 into 5. Both are primes, where both are primes. Therefore 10 can be expressed as a product of primes. The next one is 11. 11 is a prime number. 12 is a composite number. 12, I can write this as 2 square into 3. 2 square is 4. 4 into 3 is 12. Therefore, in which both are primes here. 2 and 3 are primes. That means 12 can be expressed as a product of primes. 13 is a prime number already. It is. Now 14 is a composite number. Which one we can write it as 2 into 7. In which both are primes. 2 and 7 are primes. Therefore 14 can be expressed as a product of primes. Now 15 is a composite number. 15 can be written as 3 into 5. 3 into 5. 3 and 5 are primes. Therefore 15 also can be expressed as a product of primes. 16 is a composite number. 16 we can write it as 2 into 2 into 2 into 2 4 times. That means 2 power 4 is also product of primes. Now 16, the primes involved in this product of primes is only 2 here. Now 17 is already a prime number. Now 18, we can write this as 2 into 3 square. 2 into 9, that is 18 only. This is also product of primes because 2 and 3 are primes. Therefore 18 also can be expressed as a product of primes. 19 is a prime number. Now 20 is a composite number, which we can write as 2 square into 5. that is 2 square means 4, 4 into 5, and right. Okay, this is a product of primes because 2 and 5 are primes. Therefore 20 can be expressed as product of primes. Therefore here you can check clearly, 1 is neither prime nor composite, 2 is prime, 3 is prime, the first composite 4 you can write it as product of primes. The next composite number 6 you can write it as product of primes. 8 is a composite number, you can write this as a product of primes. Similarly with 9, 10, these are composite numbers which we can write them as a product of primes. Now here also 12 you can write it as product of primes, composite number. 14 composite number it is, you can write it as product of primes. Similarly 15, 16, 18 and 20 all are composite numbers, you can write as product of primes. It means here all are composite numbers from 1 to 20. The composite numbers from 1 to 20 we can express them as a product of primes. And the way we are writing in this way of writing a composite number as a product of primes is called the prime factorization. This prime factorization, and we will know this. In 21 is a composite number which I can write as 3 into 7. 3 and 7 are prime numbers, that's why 21 we can write as a product of primes. Only 22 is also a composite number which we can write as 2 into 11. Both are prime numbers, so product of primes, you can write it as product of primes. 23 is a prime number. 24 is a composite number which you can write 2 cube into 3, that is 8 into 3 is 24 only. That means here we wrote 24 as product of primes, 2 and 3 are primes only, that's why you can write it as product of primes. Similarly 25 is 5 square, that 5 is a prime number, 5 square means 5 into 5, that means 25 you can write as a product of primes. 26 is a composite number which you can write as 2 into 13, that means product of primes you can write. 27 is 3 cube, 3 into 3 into 3 is 27, that means 27 also can be expressed as a product of primes. Let's see 28 you can write as 2 square into 7, as 2 square into 7 is 4 into 7 only, that is therefore 28 also can be expressed as a product of primes in this, those 2 and 7 are the prime numbers. 29 is a prime number, and 30 I can write as 2 into 3 into 5, all the 3 are prime numbers, that means 30 also can be expressed as a product of primes. The primes involved in this are 3 primes are there, 2, 3 and 5, whereas in 28 the primes involved are 2 and 7 only. This is 31 is a prime number. 32 is a composite number which we can write as 2 power 5, 2 into 2 into 2 into 2 into 2, that is 2 multiplying 2 5 times, therefore that is also product of primes. 32 can be expressed as a product of primes. 33 we can write 3 into 11, that means 33 also can be expressed as product of primes. Here the primes involved are 3 and 11. 34 you can write composite number, you can write this as 2 into 7, that means expressed as product of primes. 35 composite number it is, you can write this as 5 into 7, that means 35 you can write it as product of primes. Here the primes involved are 5 and 7. Coming to 36 is a composite number. You can write this as 2 square into 3 square. 2 square is 4 and 3 square is 9. 4 into 9, 36. Here the primes involved are 2 and 3. Therefore 36 can be expressed as the product of primes. 37 is a prime number. Coming to 38, we can write it as 2 into 19. 2 into 19. Here both are prime numbers. 2 and 19 are prime numbers. Therefore 38 also can be expressed as product of primes. 39 is a prime number. Now 40 we can write as 2 cube into 5. 2 cube is 8. 8 into 5 is 40. Therefore 40 is also can be expressed as a product of primes. Now we check from 21 to 40 in this slide. Here all the composite numbers are expressed as product of primes. Okay, from 21, 22, 24, 25, 26, 27, 28, 30. All are composite numbers. 32, 34, 35, 36, 38, 40. All are composite numbers, and all the composite numbers we are able to write them as product of primes. Okay, this way of writing a composite number as product of primes is called prime factorization. Now in this way we can write any composite number as a product of primes. Now let us see the fundamental theorem of arithmetic once again. Every composite number can be expressed as a product of primes, and this factorization is unique apart from the order in which the prime factors occur. Just now we check from the numbers 1 to 40. In those all the composite numbers from 1 to 40, we can write them as product of primes. In this way we can write any composite number as a product of primes. Now the other thing is, this factorization is unique apart from the order in which the prime factors occur. I'll explain what is the meaning of this one. I'll explain by taking one example. Let me take some 48. 48 is a composite number. Now I will write this as a product of primes. To write the given composite number as product of primes, we will use two methods. One is factor tree method, the other one is long division method. I will find the prime factorization, that is product of primes of 48, by using factor tree. While finding prime factorization, I express this as product of two numbers. Among those two numbers, one should be prime always. In general, we start with 2 only. Now 48 we can write as 2 into 24. Okay, again 24 is a composite number, as 2 is a prime number. 2 we cannot write as a product of any two numbers as it is prime number. 24 we can write as 2 into 12. Again the 12 we can write it as 2 into 6. Again 6 can be written as 2 into 3. Now all are prime numbers. All the numbers we got prime numbers. This cannot be continued as 2 and 3 are the prime numbers. Therefore 48 is a composite number which we can write as 2 power 4 into 3, because 2's are 4. 4 2's are there and 1 3 is there. Therefore 2 power 4 into 3 power 1. Therefore 48 can be expressed as a product of primes. The meaning of this one is, if I change the order of these two, suppose let me change 3 power 1 into 2 power 4. 3 power 1 into 2 power 4. What I will get? I will get the same number only. 3 power 1 is 3, 2 power 4 is 16. 3 16s will get 48. The same number only we will get. That means if we change the order of primes, there is no problem. We will get the same number. Therefore, every composite number we can write as product of primes, and this product of primes is not is unique, and the order of primes can be anything. The order can be changed. This is the meaning of this one. Okay, in this way you can write every composite number as a product of primes, and this is called prime factorization. Prime factorization. Okay, to find the prime factorization of any composite number, you will use factor tree method or a long division method. Suppose by using long division method, how to find the prime factorization of 48? Let's see here. Okay, I want to find prime factorization of 48. We start with 2, always prime numbers. 2 24s. Again with 2 is possible. 2 12s. Again with 2 is possible. 2 6s. Again with 2 is possible. 2 into 3. We'll get the same thing here also. Okay, here we cannot write 3 as product of two numbers. We can stop here. This is a prime number. Now 4 2s are there, 2 power 4, and 1 3 is there, 3 power 1. This is the prime factorization of 48. So in this way, we can find prime factorization of any composite number by using either factor tree method or long division method. Now let's do some problems. Express each of the following integers as product of primes. He has given some numbers. You have write these as a product of primes. As he didn't mention any method, we can use either factor tree method or long division method. Now let us I will use factor tree method to find the prime factorization of all these four numbers. Now here the first number is 420. 420 you can write 2 into 210. Similarly, 2 is a prime number. Now 210 is a composite number. We can write this as 2 into 105. Now 105 can be written as 3 into 35. Now 35 I can write as 5 into 7. Now both 5 and 7 are prime numbers. We can stop here. Okay. Now 420 I can write as those 2 2s are there, that's a 2 square. Only 1 3 is there, 3, that's 3 power 1. 5 is there, 5 power 1. 1 7 is there, 7 power 1. Now in this C, all are prime numbers, 2, 3, 5, 7. Therefore prime factorization of 420 contains 4 prime numbers, 4 different prime numbers, which is the required prime factorization. Let us see with the name 468. 468 I can write as 2 into 234. Again 234 is a composite number. This can be written as 2 into 117. Now 117 can be written as 3 into 32. 32 again 2 into 13. There's some mistake is there. 3 into this is 39. Okay, 3 into 39, 39 is 117. Therefore 39 can be written as 3 into 13. Now both 3 and 13 are prime numbers. You can stop here. Therefore 468 is equal to 2 2s are there. Okay, 2 are there, that's why 2 square. The 3s are 2, that's a 3 square into 13. This one 3 into 3 I wrote now, 3 square you can write. 2 square into 3 square into 13, in which all are prime numbers, which is the required prime factorization. The next number is 945. 2 is not possible, 945 is not divisible by 2. That's why I will go for 3. With the 3, you can write it 945 as 3 into 315. Again 315 you can write as 3 into 105. 105 you can write it as 3 into 35. And 35 you can write it as 5 into 7. Here 5 and 7 are prime numbers. Therefore 945 is equal to 3 3s are there, 1 2 3, that's why 3 cube. Only 1 5 is there, 5 power 1, and only 1 7 is there, 7 power 1. Therefore 945 we can write it as 3 cube into 5 into 7. This is prime factorization, all are prime numbers only. That's why which is the required prime factorization. And we take 7325 by using 3, 2 and 3 are not dividing this number. That's why let's go for with 4. 5. 4 is a composite number. We have to go with 5. 5 into 1465. Again, next one is 5 into 293. Here 293 is also prime number. We can stop this process here. Therefore, 7325 is equal to 5 square into 293. The 5 and 2 and both are prime numbers. Therefore, this is the required prime factorization. Now, in this way, we can find the prime factorization of the given numbers by using factor tree method. Now, determine the prime factorization of each of the following positive indices. He has given 3 numbers. Now, I will use the long division method to find prime factorization of these numbers. Okay, 20,570. Let me start with 2, as it is even number. It can be divided by 2. Okay, 2 times of 10,285 is this one. That's why. Again, then done with 5 times of 2057 is this one. No other. Next one is 2057 is not divisible by 5, 7 also. Then next prime is 11. 11 times of 187 is 2057. 11 times of 17 is 187. Here all are prime numbers. If 17 is a prime number, we can stop the process here. Whenever we got prime number here, we can stop the process. Now from this 20,570, we can write as only 1 2 is there, 2, only 1 5 is there. Okay, 5 power 1, 2 11s are there, 11 square, and only 17 is there, 17 into 17. Now all are prime numbers, 2, 5, 11 and 17. Therefore this can be expressed as a product of primes, which is the required prime factorization. Similarly, 58,500, 2 times of 29,250 is this one. The same way, 2 times of 14,625 is 29,250. As 14,625 is not divisible by 2, let's go with 3. 3 times of 4,875 is 14,625. Again, 3 times of 1625 is 4,875. Now this one 1625 is not divisible by both 2 and 3. Let's go with 5. 5 times of 325 is 1625. 5 times of 65 is 325. Then 5 times of 13 is 65. Okay, all of 13 is a prime number. You can stop the process here. Therefore, the given number 58,500 we can write as, okay, 2 2s are there, that's a 2 square. 2 3s are there, 3 square. 3 5s are there, 5 cube. Into 13 is only 1, 13 power 1. All are prime numbers, which is the required prime factorization. You can find the prime factorization of this one. Okay, also in this way, the same process you can follow the prime factorization of this number. Now here see, initially it is not divisible by 2, 3 and 5. That's why we went to 7 directly. Okay, it is divisible by 7, then 7, 13, 17, 17, 19. All are prime numbers. That means the given number is equal to 7 square. 2 7s are there, 2 13s are there, 13 square. 2 17s are there, 17 square. Only 1 19, 19. All are prime numbers. This is the required prime factorization. And make sure Here we are dividing with only primes always in this method. These should be prime numbers only. Always that can be any prime number. Okay. You have to start with the smallest prime number that divides the given number. Here 7 is the smallest prime number that divides this number. That's why we started with 7. In this way you can find the prime factorization of any composite number. Okay. Now here one more thing. The prime factorization of 20,570 is 2 into 5 into 11 squared 17. The primes involved in this are 2, 5, 11 and 17. And primes involved in this are 2, 3, 5 and 13. Primes involved in this are 7, 13, 17, 19. This way you can conclude. Okay, in this way you can find the prime factorization of any composite number by using long division method also. Now we have learnt the fundamental theorem of arithmetic. From that we can conclude every composite number can be expressed as a product of primes, which is called prime factorization, and this prime factorization also we can find by using either factor tree method or long division method. Now what are the applications of this fundamental theorem of arithmetic? We can find LCM and HCF of given numbers by using fundamental theorem of arithmetic. This method is also called prime factorization method. Now how can we find this LCM and HCF? For the given numbers, HCF is equal to product of the smallest power of each common prime factor in the numbers. LCM is equal to product of the greatest power of each prime factor involved in the numbers. And this will be clear if I will do some problems by using this formula. Now let us do one problem. Find HCF and LCM of 96 and 404 by the prime factorization method. To find HCF and LCM of any given numbers by using prime factorization method, first of all we have to find their prime factorizations. Now here the given numbers are 96 and 404. Now for these numbers I will find prime factorization first, then I will use these prime factorizations to find HCF and LCM. The first number is 96. Now to find prime factorization number 96, I used here long division method. 2 times of 48, 96, 2 times of 24, 48, 2 times of 12, 24, 2 times of 6, 12, 2 times of 3 is 6. 3 is a prime number. You can stop the process here. Therefore we have 96 is equal to 2, 5 2's are there, that's a 2 power 5, only 1 3 is there, into 3 power 1. The next number is 404. You can write 2 times of 202 is 404, 2 times of 101 is 202. 101 is a prime number. You can stop the process here. Therefore 404 you can write 2 2's are there, that's a 2 square, into 101 power 1. Therefore we calculated the prime factorizations of both the numbers. Now let us see how to find HCF and LCM by using these prime factorizations. Okay, here the HCF, product of the smallest power of each common prime factor in the numbers. That means here the prime factors involved in the prime factorization of 96 are 2, 3, whereas the prime numbers are the primes involved in the prime factorization of 404 are 2 and 101. Now to find HCF we will use common prime factors, okay, or common primes. Now here the 2 is the only common prime. 2 is the only common prime. Okay. have to take product of the here we have taken common prime factor. Now for this what you have to do, you have to take the smallest power. Now the common prime 2 is having power 5 in 96, power 2 in 404. Therefore you have to take smallest power. Therefore power 2 I should take. That means I will get 2 square. Okay, 2 is the common prime. Its powers are 5 and 2 in the numbers 96 and 404 respectively. Among those I should take the smallest power. That's why 2 I have taken. Therefore 2 square is equal to 4. HCF I will get 4. Similarly, let's go for LCM. To find LCM, product of the greatest power of each prime factor involved in the numbers. Therefore, we have to take all the prime numbers. 2 into 3 into 101. Okay, 3 primes are there. Combinedly, 2 is there, 3 is there, 101 is there. We have to take all the primes and their greatest powers. The powers of 2 are 5 and 2. We have to take the largest power, 2 power 5. Into power of 3 is only 1, 3 power 1, and in 100 power 1, 101 power 1. That is, by multiplying this, we will get 9696. This is the required HCM. Here, remember one thing: while finding HCF, we take only common prime factors. We take only common primes. Whereas while finding LCM, we will take all primes. This is important. While finding HCF, we will take smallest powers. While finding LCM, we will take the greatest powers. Now let us see one more problem. Find the HCF and LCM of 6, 72 and 120 using the prime factorization method. Now first of all, we will find the prime factorizations of these numbers by using any method actually. Now here I am using again the long division method. We have 6 as 2 power 1 and 3 power 1. 72 also by using long division method. 72 I got it as 2 cube into 3 square. 3 2s are there and 2 3s are there, 3 square. Now 120 you can write as 2 cube into 3 2s 2 cube into only 1 3 is there, 3 power 1, 5 is there, 5 power 1. Now I got all the prime factorizations of these numbers. Now to find HCF, we have to take the common primes. Now 2 is there in all the 3 numbers, 3 is there also in all the 3 numbers. Only 2 and 3 are the common primes. And their smallest powers I should take. The powers of 2 in all the 3 numbers are 1, 3, 3. I will take 2 power 1. The powers of 3 in all the 3 are 1, 2, 1. The smallest is 3. Therefore 2 power 1 into 3 power 1 is my HCF. Let's see product of the smallest power of each common prime factor in the numbers. That is 2 power 1 into 3 power 1, that is 6. We have to take only common primes. Similarly LCF, while using LCF we have to use all the primes. All the primes I will have are 2, 3 and 5. For 2 largest power is 3. For 3 largest power is 2. For 5 largest power is 1 only. And by simplification I will get 360. Here I used all the primes for LCM, common primes for HCF. Let's take one more problem. Find the HCF and LCM of 48, 72 and 108 using the prime factorization method. The same process. We have 48 is 2 power 4 into 3 power 1 and 72 is 2 power 3 into 3 square, whereas 108 is 2 square into 3 cube. Here the primes involved in this are 2, 3. Here the primes involved are 2, 3. Here also primes involved are 2, 3. Therefore the common primes are 2, 3. The powers of 2 are 4, 3 and 2. I should take the smallest power, square. The powers of 3 are 1, 2, 3. Smallest one is 1. Therefore 2 square into 3 power 1 is my HCF. The HCF is product of the smallest power of each common prime factor in the numbers. Therefore 2 square into 3 power 1 is 12. LCM is product of the greatest power of each prime factor involved in the numbers. Now each prime factor here are 2 and 3. These are the only prime factors. we have to take greatest power. Greatest power of 2 is 4. That's why 2 power 4 into greatest power 3 is 2, 3. That's why 3 cube. Then the LCM. Therefore 2 power 4 into 3 cube, that is 16 is 27. I'll get 432. In this way you can find LCM. One thing, in case of LCM, you will use all prime factors and greatest powers. In case of HCF, we will use only common primes and their smallest powers. Find the missing numbers A, B, C and D in the following factor tree. He has given a factor tree where some unknowns are there. You have to find them. Now these are the unknowns A, B, C and D. Okay, we have to find this. And by using factor tree, we know 9009 is the product of A and 303. We know that. That's right. A into 303, I can write 9009. From this, A is equal to 9009 by 3003. That is 3 times we will get A. A value is D here. And similarly, use this one. Okay, B into 243. B into 143 is 1001. B into 143 is equal to 1001. From this, B is equal to 1001 by 143. That is 7 times of 143 is 1001. If B is equal to 7. Similarly, 143, here two numbers are not given. We have tried, because all should be prime numbers, we know. C and D should be prime numbers. This is the use of prime factorisation. Then only we will stop the factor tree. Therefore, 143 I can write as 11 into 13, where both are prime numbers. That's why C is equal to 11 and D is equal to 13. So in this way, you can find the unknowns whenever there are some unknowns in the given factor tree. In this class, we have learned fundamental theorem of arithmetic, which is every composite number can be expressed as a product of primes, and this factorization is unique apart from the order in which the prime factors occur. And we discuss some applications of FTA, that is finding LCM and HCF by using FTA, that is prime factorization method. And the formula for finding HCF and LCM are product of the HCF is equal to product of the smallest power of each common prime factor in the numbers, whereas LCM is product of the greatest power of each prime factor involved in the numbers. While finding HCF, we will use only common primes and their smallest powers. While finding LCM, we will use all primes and their greatest powers. Okay. In the next class, we will discuss the relationship between LCM and HCF and some problems on fundamental theorem of arithmetic. Thank you.